I guess we can start. Yeah, so we were discussing the basis of small disturbance approach in hypersonic flow. We'll advance it further today. We'll take few sessions to complete it. But today we'll continue from where we have stopped as the introduction to the topic. Now, as we have seen already, and as you are familiar from the fundamentals that you had for small perturbation approach in aerodynamics in general, the whole concept is based on the response of the flow to a small disturbance. So wherever we can approximate the flow deflection to be small, I repeat that, wherever we can approximate the flow deflection and the concomitant velocity variations from the mainstream components to be small relative to the mainstream components, then we have a chance to apply the small disturbance approach or small perturbation theory. That's how it is done in aerodynamics in general, and that's the same thing we are going to extend to the hypersonic region. Now, in hypersonic flow, this is particularly useful because the hypersonic designs, as far as breathing concepts are concerned, they are going to be as of now. That is, wherever we are at present, the global body of knowledge. The design is going to be, of course, we know that it's a futuristic idea. I have a video which I'll try to share at the end of this class, where Boeing explains where they stand now and what are some of the future plans that they have for hypersonic flight. And it's going to be fairly somewhat distant reality. But then all the current designs that people have in mind are relatively thin. That is, they are going to be more like slender bodies than blunt ones. Okay. So this slender body aerodynamics is going to be of particular interest in applied hypersonic aircraft propulsion. And that's one reason why some of these approaches that we are discussing are going to be still useful despite the main constraints that they have in terms of the assumptions involved. Okay, so with that preface, I don't know whether I described this particular slide in the previous class. Sorry, did I explain this? That is how we are going to non-dimensionalize the velocity as well as the length. Somebody please. Did I present this slide in the last class? I think I just stopped at this. Nobody's sure. Anyhow, so I'll just start from here. A perturbation means, as you know, a change in velocity. In fact, a change in any flow parameter for that matter. We are going to focus on velocity. So we are just talking about velocity. So in our discussion, perturbation means a change in velocity with respect to the mainstream velocity. So you have a mainstream flow approaching the body at a velocity v infinity. That is the mainstream flow coming at v infinity. We are considering a body here where we are assuming it is slender enough to have an attached shock. And now, what is our interest? Our interest is in predicting or having tools that can help us estimate the pressure distribution, static pressure distribution along the wall of the body. of the entire body. So for this consideration, we are just looking at an zero angle of attack. Okay, so you have a mainstream flow V infinity, which is taking place over the body, and we know that there is going to be variations. This we have discussed about U and V components. U is the variation in the mainstream velocity, which becomes V infinity plus U dash. U dash is the disturbance, the perturbation. That is the variation in the mainstream velocity. Similarly, V, the y velocity component is going to be V dash. Why V dash? Because to begin with, the flow is along the x-axis. It does not have a y component. So there is no free stream component for y velocity. Y velocity is induced only as the flow takes place over the body. Now, our assumption is that u prime or u dash, that is the velocity induced in the x direction, is much smaller than the mainstream velocity, and so is the y component. The y component of the disturbance v dash is significantly lower than the mainstream component. Of course, these can be higher than. I mean, they can be comparable to, or they can be. They need not be smaller as compared to the sound velocity, but they are smaller than the free stream velocity, which is certainly much higher than sound velocity, since we are talking about hypersonic flows. Okay, now when we need to also incorporate the geometry of the body. For that, let's look at this expression here. The velocity, the body surface is going to be considered as y being a function of x. Y, that is y coordinate, as a function of x. Now, if so, the dy by dx for the body of the surface, y equals fx is the body surface. Dy by dx can be stated as a ratio of the changes in y component of velocity to the x component of velocity. Changes. Now, what is the change in y component of velocity? Y component of velocity to begin with was 0, and it becomes v dash. So v dash by v infinity plus u dash. That is the new velocity in the y direction is v infinity plus u dash. It was originally v infinity, but because of the body, there is an increment which is u dash, which is in. So then the net velocity, or the the net velocity in the y in the mainstream direction, the x direction, is v infinity plus u dash. So v dash divided by v infinity plus u dash can be equated to the slope. Now, where is this coming? That you can understand that more readily from the picture. The v dash is marked here. I hope you are able to interpret the meaning of v dash there. It's a y component of the velocity. Okay, and v what is the x component of velocity? It's v infinity plus u dash. Okay, now the slope of this body, that is dy by dx. I said that y equals fx is the the surface of the body. So the slope of the body at one point is dy by dx, which can be equated as v dash by v infinity plus u. That can be considered. That can be understood by just considering this triangle here. You have v on one side, v infinity plus u dash, and v infinity plus u dash, and v dash on the other side. V, this velocity is the velocity downstream. So the resultant velocity. So with this, we can relate that v dash by v infinity plus u dash is the slope of the surface. So what are we doing by equating this? We are relating the change. We are relating the velocity field to the shape of the body, or to the geometry of the body. Now comes the all-important parameter, the tau, which is defined here as a d by L. What is D? The transverse dimension. Could be, if it's a conical one, it can be the diameter. So the transverse dimension D and the streamwise dimension L, the ratio of the two, D by L. You would have already heard of the parameter, the property called slenderness ratio. Slenderness ratio, which is L by D. Actually, it's very important, not only in aerodynamics, even in structural analysis. Probably you would have come across that in aircraft structures, etc. The slenderness of a shaft, etc., is an important parameter in studying, analyzing the vibration and internal stresses and the stresses produced by bending moment, etc. So what we mean by slenderness ratio for this particular body is the L by D of it. L divided by D. Now tau, the way that tau is defined is D by L. So the inverse of slenderness ratio. Okay, so the geometry parameter that we are going to consider is the non-dimensional parameter D by L, which is the inverse of slenderness ratio. I will call it as blunt, a measure of the bluntness. Now, bluntness probably is not a familiar word. I don't even know whether it is there in dictionary, whether it is grammatically correct, etc. But for the convenience of our discussion, I may repeat the word bluntness. What I mean is the inverse of slenderness. Why I need such an odd looking word is because tau is defined as D by L. So it's a measure of how blunt the body is. Higher the value of tau, the higher is the blunt nature of the body. So we may have to refer back repeatedly this parameter tau. So I may keep referring to it as bluntness of the body. Okay, a non-dimensional parameter that reflects the bluntness of the body. So tau is D by L. Now, just completing the description, dy by dx is the slope at any point of the body, which I mentioned already. And now please look at the white box, the new one here, at the lower one. V dash by V infinity plus U dash. V dash by V infinity plus U dash. V dash is the induced velocity in the y direction. V infinity plus U dash is the new velocity in the x direction. The ratio of that, as we have already seen, is dy by dx. Now, what is dy by dx? The dy by dx, the parameter itself, by the definition of it, it's a change in y divided by change in x, which means that it's going to be the order of the of this parameter that we have defined already. It's going to be of the order of d by L. D, the change in y, or rather the dimension along y, and L, the dimension along x. So dy by dx is going to be of the order of dy by dx is going to be of the order of d by L. I'm not saying that they are equal. They are going to be of the order of. Now, what is meant by this notation? This is used here to indicate as of the order of. So this notation we are using to indicate of the order of. Of the order of means of the order of magnitude. Order of magnitude analysis, I'm sure you're familiar with that. So when you say dy by dx is of the order of tau, it only means that the values, the ranges that it falls in are comparable across, or rather within the same orders of magnitude. So this is what we are taking primarily from the discussion on this slide, that that is the dy by dx can be of the order of tau, the inverse of slenderness ratio of the body. Shall I move forward, or should I clarify anything further on this slide?
You can go to the next slide, sir.
We'll continue. Yeah, these are a lot of such expressions and equations, etc. If at any point anything has to be revised, I'll be happy to do that. But for now, I'll just keep going. So we have a set of equations here, but if you look at them, they are familiar. We have already referred to them. Only thing that I have done now is to rewrite them in terms of the perturbations. So for example, if you look at the first one, the continuity equation, dou rho by dou rho v by dou x plus dou rho v dash by dou y, dou rho w dash by dou z. That we have just written that instead of rho the first term, I have just written it as, or the way that we are using here, the first term is modified as rho v infinity plus u dash. Now why v infinity plus u dash? We are rewriting the equations in the using the perturbed variables. Okay, are we justified in doing this? Yes, because they are the governing equations which should be applicable everywhere in the flow field as long as the flow is steady and inviscid. Keep in mind, the form of equation that we are dealing with are steady inviscid forms of governing equations. So as long as the flow is steady inviscid, we can use these equations. So we are now applying these equations to the perturbed flow field. So when I am using it to the perturbed flow field, I can use, instead of velocity, I can express it as the new velocity terms, which I have already rewritten in terms of the perturbed velocity. So what is the y component, x component of velocity? The perturbed velocity is v infinity plus u dash. U dash is the perturbation. U dash is the small disturbance. So v infinity plus u dash is the new velocity. So the first term, instead of dou rho v by dou x, I write it as dou rho v infinity plus u dash by dou x. Similarly, the second term is, what I need there is the y velocity. But the y velocity, I know that is the perturbation that is created by the body. Why? Because initially the flow was aligned with the x-axis, so there was no y component. So all that I have for y velocity is v dash, which is the small perturbations created. Similarly, in the z direction also, the perturbation, smallness of the perturbation applies for both the dimensions, x as well as y. So for z, I just write it as rho dou by dou z of rho w dash, and that's the energy continuity equation. Now I make similar changes in the momentum equation also. In the momentum equation also, where I am replacing all the velocities by the perturbed forms of them. There, instead of rho v, v, I am writing rho v dash, because I know that v is equal to v dash in the perturbed flow field. Similarly, rho w dash, etc. Keep in mind that we are rewriting the perturbations, or rather, we are rewriting the equations incorporating perturbations only to the velocity. We are not disturbing density and pressure. Say P, I am just writing as P. Rho, I am just writing as rho. I am not writing P plus P dash. I can do that actually. We can rewrite the whole thing using pressure disturbances also, or pressure perturbations also, and also incorporating rho this ones, which is actually not required at this stage. So we are not doing that. We are or in other words, we are rewriting the equations by incorporating perturbations into the velocity components and only to the velocity components. Nothing wrong in writing it in incorporating the pressure perturbations also. We don't require it for the present theoretical formulation. So we are applying the perturbations only to the velocity. So you have the x component of momentum equation, or y component, and the z component of momentum equations. We also have the energy equation. In all these equations, we have replaced velocities by the respective perturbed components. So these are the governing equations in perturbed form. Okay. Now the next step is to non-dimensionalize them. What's the function importance of non-dimensionalization? We have discussed it already. Non-dimensionalization, we will be able to make the analysis independent of the geometric dimensions. So, and also here in perturbations theory, non-dimensionalization has even more utility as we are going to see soon. But then let's first understand that when we are looking at the non-dimensional parameters, we will be first focusing on the slenderness or the inverse of slenderness, tau, d by L, which is less than 1. T by L, that is the length, the diameter, the transverse dimension divided by the length dimension. It has to be less than 1 because we are assuming slender bodies. Slender bodies, that is L by D is L by D is high, which means that D by L has to be low. Bodies which are long than being long and thin, as opposed to say thick and short. This is a blunt body. That this is a thin, slender body. So D by L is very small, or in other words, is smaller. In other words, tau is very small. So needless to say, if tau is small, tau squared will be much smaller. So as as tau becomes smaller and smaller, less than 1, tau squared tends to be 0. Okay, so this means that if I have tau squared tending to be 0 or tau being very small, the governing equations can be non-dimensionalized in such a way that they will have terms which are of the order of unity, and they will have terms which are of the order of tau squared. I repeat this. If I can non-dimensionalize the governing equations appropriately, I can achieve terms which are of the order of unity, and I can have terms with tau squared, which, as we have seen here, is very small, is much smaller than unity. Or in other words, if I have equations non-dimensionalized in such a way that some terms are of the order of unity and some terms are of order of the order of tau squared, then the terms which are of the order of tau squared can be neglected because they are going to be less than unity, and other terms are of the order of unity, which means that in comparison, the terms which are combining are having order of tau squared can be neglected. I'll just try to explain. I don't know where I'm talking in the air, but I'll just try to explain it a little bit using an example, one particular variable. We know that v dash is much less than v infinity. Remember this. Why am I saying this? Because v dash is a transverse disturbance, is a disturbance in the y direction. We know that for a slender body, this can be assumed to be much smaller than the approaching free stream velocity. So v dash is much smaller than v infinity, which means that v dash by v infinity, it's a non-dimensional parameter, right? V dash, that is the y disturbance, a perturbation in the direction of y, perturbation in velocity in the direction of y, divided by v infinity, the free stream velocity, is much smaller than 1, right? V dash is much smaller than v infinity, so v dash by v infinity is much smaller than 1. Again, so if I have a parameter like this in the equation, I can assume that to be much smaller than 1. Again, now what if I multiply the denominator by tau, that is v dash, I'm sorry, small v dash, v dash divided by v infinity. This is smaller than 1, right? That's what we see here. But if I multiply the denominator by tau, That is V dash by V infinity into tau. I repeat that, V dash by V infinity into tau. That is the denominator I'm multiplying by tau. Tau is by itself a small parameter because it's d by L, and d by L is less than 1 because it's a d by L is less than 1. So tau is less than 1 because we are considering a slender body. So we are multiplying the denominator by a parameter, a value which is less than 1, which in turn can have increased this the value of this function because we are multiplying the denominator by a parameter that is lesser than 1. So the net value of v dash by v infinity into t can be of the order of 1. Otherwise it is v dash by v infinity is much smaller than 1, but now we are multiplying the denominator by a fraction so that the whole order of magnitude of this can be approximately, or that can be considered to be of the order of 1. So v dash by v infinity into t can be of the order of 1. So this is what we are, so what we are now doing is parallelly, concurrently, we are using non-dimensionalization and an order of magnitude analysis. Okay, I think I should stop here. We will continue this actually because we need to gradually go into the equations back and forth and then apply or make sense of these simplifications and then try to relate that to the observation. So that's going to be the path that we take in this small perturbation analysis. We'll continue with that. I'll stop to here. I'll try to play a video, but before that, if you have any questions, you may please ask. Sorry, but can you see and hear the video? I'm trying to share it from my mobile. So I just want to be to confirm whether the audio is whether you're able to hear hear as well as see. Can somebody please confirm?
So nothing is visible or audible.
I see. Okay. Then there is an issue. Yeah. Thanks for that. I'll try to do that again. Okay. I thought I started sharing the whole thing once. How is it now? Are you able to hear or see or both or what?
Most okay. I can't hear anything.
Same with everybody?
Yes, sir. It's visible but not audible.
Oh, sorry. Then I'll share. Why should it so? Why should it be so? Mm. Okay, then. So you can. I'll share that on the MS Teams file folder or somewhere. I'll upload it. I request you to go through it. Now, this is not a very highly technical video. Actually, it's like a popular. I think it's part of a TV show or something. But what is important for us in that is to note what are some of the uh, body kind of relation. What kind of a body do they envisage for hypersonic flight? So this from the uh, perspective of Boeing. Actually, they are actually. I'll just stop the video. They are trying to say, or they are. I mean, in this video, they are showing a model. Actually, I think it's a different video that I wanted to show, which I'll do that. I'll upload that particular video or link, YouTube link in the, I guess it is this. Which you can see later. But what I want you to focus is on the kind of shapes. You would have seen them already, but I just want you to look at them from the perspective of the discussion that we have. That is the slenderness. Basically, that's the reason why I want to bring this video in this context. That is the kind of shapes that which are actually somewhat significantly different from the usual aircraft models that we have in use currently, because in hypersonic flow, because of several other constraints, the shapes have to be different. And as far as we can see, or as far as we can think now, they are all going to be very slender. Okay, so the D by L, or the bluntness ratio that we are discussing currently, are going to be significantly small for bodies of interest in air breathing propulsion in hypersonic fields. So that's one reason why we are still concerned about, or we are still interested in such simplified approaches of analysis, which can give useful insight and useful values for pressure distribution on slender bodies. We'll be continuing the discussion on slender bodies and the perturbation analysis in the coming classes. Meanwhile, I request you to go through this video also. Okay. Since it is not playing well, I'll upload it. I request you all to go through it at your time. Now, any other questions or anything that we have to discuss today? No, I have no idea why it is not even playing now, because I tried it a while ago. It was okay. Playing now. I don't know whether you are you able to hear the audio by any chance?
No, sir. Nothing.
You said no or yes?
No, nothing is audible.
Oh, okay. Okay. You can see it later. Then I'll upload it. I mean, as I said, it's not a very technical one, but then some of the points that they are trying to make in this are important from our perspective also. So for example, going to talk about what is going to be the materials and why it should be high temperature resistant, etc. Why it cannot be aluminum, etc. So some of these are informative to us, to our context of discussion also. Stop it here. Okay. So if you have any questions, we'll take right away. This will stop for the day. No questions, and we'll stop here today. Thanks to all of you. Bye.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir.